Hey, how's it going everyone? Welcome to the next video. Today we're going to have a look at planar graphs and on the Euler's formula. So to start things off, a planar graph, I haven't written it in, but is a special kind of network or graph. So the additional properties of a planar graph will allow us to map two-dimensional and even three-dimensional objects into graphs. So to start things off, we've got what's called a degenerate graph. So these are worth adding to your glossary of definitions. So basically, a degenerate graph is a graph with no edges or connected to any of the vertices. So on the side, we've got a little example. So we've got 1, 2, 3, 4, and 5, and we've got no edges between them, so it's called a degenerate graph. The other situation is we've got a complete graph. So a complete graph is where all the vertices are connected to every other vertice in the graph. So if we have a look at vertex 1, it's connected to 2, it's connected to 3, it's connected to 4, and it's connected to 5. As with 2, so 2 again is connected to 1, 3, 4, and 5, and etc. So that's called a complete graph. It's where all the vertices are connected directly to every other vertice. So for a complete graph, we had a look at last video. E is what we label as our edges, and vertices is V, capital V. So for a complete graph, if the number of edges and the number of vertices, if E equals the number of vertices, edges, and V equals the number of vertices, so we've got this formula, V times V take 1 over 2. So just as an example for this one here, we had 1, 2, 3, 4, 5 vertices, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, so there's 10 edges for that one. So E, if it was a complete graph, we had 5 vertices, 5 vertices take 1 over 2. So 5 take 1 is 4. 5 times 4 is 20. 20 divided by 2 equals 10. So if I had 5 vertices, if it was a complete graph, I would have, through the formula, 10 edges. So we've seen from this past quick example here, we had 5 vertices, we had 10 edges, therefore from the formula it can be said that that graph is a complete graph. So that's how we determine if they are complete or not. So looking at planar graphs, a planar graph can be defined as followed. Basically, a graph which has no edges that cross each other is the simplest way of looking at it. So if I have 4 vertices, this would be a planar graph. It's not a complete graph, but it's a planar graph because I have no edges that cross each other. Now, if I had a vertex that went, or edge that went from that one to that one, and I had one from that one to that one, as you can see, we've got 2 edges that cross. Therefore, it doesn't look like it's a planar graph. However, I can manipulate this graph a little bit. So I've still got the same edges to the same vertices. So on the outside, these are going to stay the same. This one here, I'm going to keep in the middle, but I can actually redraw this edge here going around the outside. So in this case, now it is actually a planar graph. So we can manipulate them a little bit. That doesn't always work. So that's basically a planar graph. So you've got three little examples here. We need to determine whether they are a planar graph or not. So as you can see for this one, pretty obvious, there's no edge that crosses another edge, so that one is a planar. This one here doesn't look like it's a planar graph because we've got A to D crossing B to C. But as I said before, A, B, C, D, I can actually redraw that crossing of the edges. I'll keep that one that goes down there, but I can draw that one going around the outside. So it is not, oh, it is a planar graph now. If you left it as that, it's not. And last one here, have a go yourself. Is that one a planar graph or not? Have a go, see if you can work it out. So we've got oops. So we've got the 6 vertices. This one's connecting there, that one's connecting there. They're probably not going to change. This one here, I can connect as shown. Alright, and the one down the middle can stay there, but I can connect that one around the outside. So now it's a planar graph. Right, but if I left it as that, it's not. Talking about regions of a planar graph. So I've got this graph here. And because the area inside these three vertices are is a solid connection, okay, basically I can color it in inside, alright, meaning that is there for a region. And I can do the same thing for this one in here. So that would be region 2. But over here, I don't have a connection between those two. So I would end up coloring in everywhere, basically around. So that would be the third region. And that's it. So just talking about regions, it's can you color in the region bounded by the vertices. I've had a look at converting non-planar graphs. So as we said, although although it may appear that a graph is not planar, by modifying the graph it may become clearly planar. So there's no specific method to doing this, as I was showing before, a little bit of trial and error, and it's possible to remove all the crossing paths. So have a go at worked example 6, see if you can convert the graph into a planar graph, indicate the faces or the regions of the planar graph. So pause the video, have a go yourself. Alright, once you've had a go, let's have a look at the situation. So we've got 1, 2, 3, 4, and 5. We've got a connection between 1 to 4. We've got 1 to 2 and 3. There's one that goes from 2 and 4. Now this one that goes from 1 to 3 crosses 2 to 4. So I actually want to go around the outside so that it doesn't cross. And we've got one that goes from 3 to 5. So I'm going to go around it so I don't again cross that path from 2 to 4. And then we've got one that goes from 4 to 5. So there's a situation where I've converted the non-planar graph into a planar graph. Again, your situation might be different. And just colouring in the edges again, sorry. So the faces, well, I've got one face here. I've got one that goes in here, and then the third one would be around the outside. So the degree of each face is the number of edges defining that region. So consider the last figure in worked example 6. Alright, mine was slightly different. It's a bit of a mess actually. Alright, but if we did it nicely, it would look something like this. So as I said before, we've got region 1, 2, and 3. Alright, 1, 2, and 3. I just didn't label it. So face 1, oops, talking about this region in here. So it's defined by the edges 1 to 3, 3 to 5, 5 to 4, and 4 to 1. So its degree would be 1, 2, 3, and 4 because there's 4 edges connecting to it or around it. For face number 2 or region number 2, we've got 1, 2, 3, 4. So its degree would also be 4. I'm not going to list them out. You can do that if you want. So the degree would be 4. And then for face number 3, well, even though we go all the way around the outside, we've got 1, 2, 3, and 4 edges touching it. So its degree would also be 4. So there's a situation in almost all cases, each region will have a degree of at least 3. So just as a bit of side note, so in almost all cases, each region will have a degree of at least 3. So the question is, why? And can you think of exceptions? So have a think about that, bring it to class, and we'll have a discussion. So why and can you think of any exceptions to that case? Number 7, find the degree of each face of the graph shown in the figure on the right. So first thing, label your faces. So I'm going to label that as 1, 2, 3, and 4. So face number 2, sorry, missed 1. 1, 2, 3, and 4. What's the degree? Okay, have a go yourselves. So the degree of each, pause the video, work it out. Okay, should have noticed I've actually missed one. So I hope you picked up on that. Missed one on the outside, which is 5. So degree number 1, or face number 1 has degree was 1, 2, 3. For number 2, again we've got 1, 2, 3, and 4. For 3, I've got 1, 2, and 3. For number 4, I've got 1, 2, 3, and 4. And then number 5, I've got 1, 2, 3, 4, 5, 6. Worked example 8. So we've got a figure on the right which looks like a cube, and we've got vertices A to F. And the question is, how can I convert this to a planar graph? So at the moment we've got a 3D image or an object. First thing, I've got to convert it into a 2D object. And although it might sound like a difficult task, it's not too bad. So I've got I'll just write them out, A, B, C, D, and we've got E, and F, and G, and H. So there's all my vertices. And this is actually going to end up really ugly, I think. But first thing, just draw out the vertices. So from A, where does that connect to? I've got one that goes to D, one that goes to A, E, and one that goes to B. So just draw your connections. So one that goes to D, one that goes to E, one that goes to B. Then moving on to B, I've got one that goes to A, one that goes to C, and F. So I've already got the A. I've got one that goes to C, and one that goes to F. From C, I've got one that goes to D, one that goes to G, and one that already goes to B. So I'm just going to pause the video here and fill out the rest. Have a go yourselves, so you pause the video here as well and see if you can fill out the rest of that situation. Okay, should have something that looks like this. Now it's actually not too bad, but the problem is it a planar graph at the moment? So the obvious answer to that is no. It's not, because we've got edges that cross each other. So the problem is, or the situation I want you to have another go at now at, is how can I convert this network into a planar graph? And it is possible, believe it or not. So pause the video and just see if you can play around and work out a possible way that you can convert this network into a planar graph so we have no edges that cross each other. Okay, so if you have a look at the face indicated here, so we've got DCAB. So just looking at that face there, forgetting about the three-dimensional part. So that face there would be a two-dimensional square if I was to draw it out. Now, so I'll say that's 2D at the moment. The thing that makes an object a three-dimensional, or converting that two-dimensional to a three-dimensional, is the possibility of connecting the same two-dimensional shape, so H, F, G, and F, and it's connecting every vertex from itself to the next object. So from D, I want to be able to have a connection between D and H. As with C and G, E and F, B and F. So that's what makes it a three-dimensional shape. So now at the moment it's a three-dimensional shape. So connecting every vertex to itself almost, in a way. Now this actually might look a little bit nicer now than that one, if you can see. So I'm almost there. I've still got some edges that are crossing each other. So just going to pause the video again and redraw a similar object. Okay, on the side, I've got my original 2D shape, A, B, C, D, and now I'm just putting the vertices on the outside of that shape. So as you can see, connecting D to H is simply a nice little connection between them there, as with C to G, B to F, and A to E. Now on the outside, I've got H to E, E to F, F to G, and H to G. So now I've got a planar graph. I don't have any edges that are crossing each other. Alright, so now that's a three-dimensional shape. So just as a bit of an extension, I can talk about four-dimensional shapes by doing the same situation. So a four-dimensional shape would be the same object here. So what do we got? So we've got I, J, K, and L, M, N, O, and P. So believe it or not, I can actually draw a four-dimensional shape using this same idea. So there's my second object, and now I just connect. Right, it is not going to look very nice. Alright, so that would be a four-dimensional shape because I'm connecting every vertex in the first one to a second one. There's not really an easy way to draw that, but it's the same idea, so then I can draw a five-dimensional shape by taking this one, connecting it again to another, etc. And basically I can go to infinity. It's just that it's not practical and it's hard to visualize four-dimensional shapes. We're good at visualizing three-dimensional, not so much for four-dimensional and so on. So that's essentially that example. So I think that's about it. Oh no, we've got, sorry, Euler's formula. So it's clear by now that we've got mathematical relationship between vertices, edges, and the faces. In fact, it is the same relationship known as Euler's formula that you may have learnt by studying geometry. We haven't had a look at that in this course this year, but you might have seen it in the past. So we've got the vertices. So number of vertices is equal to the number of edges, take away the number of faces, plus 2. So a little definition for you. So last one, verify Euler's formula for the cube in the last figure in worked example 8. So if we have a look over here, it was this one here. So the number of faces, we've got 1, 2, 3, 4, 5, and 6 faces. We've got 1, 2, 3, 4, 5. So it's 12 edges. So 6 faces, 12 edges, 8 vertices. So using that formula, we've got V equals the number of edges, take away the number of faces, plus 2. So the number of vertices we said was 8. And number of edges we said was 10. No, 12, sorry. So we got 12. Number of faces was 6. And we add 2. So 12 take 6 is, 12 take 6 on a good day is 6. 6 plus 2 is 8, which is what we had. Alright, so that's all we need to do for that. So that's chapter 9.3. Have a go at the questions. Stay tuned for the next video.